What we can do now is give it back over to Bailey, our fearless keynote leader, to talk about machine learning. So, Bailey, go for it.
Great, thank you. Yeah, as you probably are aware, AI and ML is a very hot topic right now. And I wanted to be able to break down and give a sort of a simplified overview of all the different approaches that I've been seeing. I'm going to focus here specifically on inferencing style workloads. And one of the things that I find most interesting about this is that WASM is an excellent compilation target for these types of workloads. And there are basically four main categories that I'm going to walk through: WASI-NN, WASI Web GPU, compiling models to WASM, and then also writing your own custom interfaces and providers. And I want to note that all of these different approaches are also compatible with wasmCloud, but I'm actually going to give many different examples that I'm seeing around the industry today. So for WASI-NN, it is a WASI interface for performing ML inferencing. It's been around for a couple of years, actually. One of the key champions, Andrew Brown from Intel, has been pushing it forward and evolving the spec for it over quite some time. We've had some very recent and very cool additions to that spec to make it a little bit better for the types of inferencing that I'm going to demo in a second. It has many different key pros. It integrates actually with your existing models and ecosystems that we have today. That space has exploded. So trying to create something that allows you to sort of abstract all of those is really incredible. That's one of the biggest strengths of it. Of course, it's a WASI API, which means that we're seeing many different runtimes implement it, from WAMR to WASM-Time and WASM-Edge. And by far, the biggest strength for WASI-NN is that it allows for hardware optimization, and that essentially you tell the API to load your model and then run inference on it. And that inferencing side actually happens with host code, with native code. That's both its greatest strength and its greatest weakness. The reason why it's a bit of a weakness is that it makes it very difficult to sandbox, and also because it ties itself to hardware, it makes it not portable. However, if you are deploying your own inferencing models, it's your first party code, then perhaps sandboxing is not as big of a deal to you. And if you already have an ecosystem that has this large investment in existing models and complex use cases, WASI-NN is a great solution for you. The other one that's emerging, but really, if we're being frank, it's very nascent, but I get asked about it a lot, so I wanted to give a bit of an overview of it. This is another new WASI interface called WASI Web GPU. And given the name, you can probably guess that it's based off of the Web GPU API, and obviously targets GPUs directly. Because it targets GPUs directly, that means that you're probably not going to have some type of CPU fallback or be able to take advantage of specialized hardware like TPUs that make it very efficient for running TensorFlow. However, its biggest pro is that it's extremely portable. A lot of places have already figured out how to support a web GPU API. It also is a lower level fundamental building block, and I find that extremely exciting because what I expect to happen is that many different people are going to build AI frameworks on top of WASI Web GPU. However, that hasn't quite happened yet, so there really aren't many off-the-shelf solutions for it today. Now, if you're a pioneer or a bleeding edge seeker, this is probably the time to jump on this bandwagon and see if you can build out your own AI framework for other people to use. Now, this is another case that I think is actually probably something that you've run and you just didn't realize. That's because TensorFlow.js seems to appear just about everywhere in major web applications. It's very handy for, let's say, blurring your video background. Now, there's another case that I think is interesting that I'm seeing a little bit more on the server side, which is compiling Llama uh, 2 specifically, so a quantized version of that model to WebAssembly. And when you compile the model and all that it contains into a single .wasm, that's really nice because that means any WebAssembly runtime is able to run it. And that allows you to do local first style workloads. You don't have to make a network request to run your inference. You don't have to step out to a separate process. It is literally all local. And that means that it's all sandboxed inside the WebAssembly runtime. Now, there are some significant trade-offs for this. The performance is probably the biggest. Inside WebAssembly, we've been pushing forward SIMD 128, so an expanded SIMD. So there is new performance gains, but at the end of the day, you're not able to take advantage of specialized hardware that loses the portability of WebAssembly by using this approach. And it also expands the code size footprint quite a bit. So if you are interested in this type of approach, which many people do because they're targeting the web or edge or local first use cases, do make sure that you use a quantized version of your model, aka something that's more compressed and smaller. All right, this last bucket here, I'll admit, is very much a catch-all, where we're seeing people write custom interfaces and providers. And the degrees of what this implementation looks like varies wildly. But I want to just give a shout out for a few different approaches. wasmEdge has a number of different styles of how they can support AI inferencing. One of those is with a TensorFlow interface. So in a lot of ways, that's like a lower level API that's very specific to TensorFlow. But if you are running with only TensorFlow, then maybe that's the best API for you. There are also lots of other cases that I'm seeing where WebAssembly components surface an open API, open AI HTTP interface that other people are able to call into. But what happens underneath is still a little bit of a varied story. How they actually are doing the inferencing seems to be very widely different between different providers. And this last one is one that I want to dive in a little bit deeper. Some folks are building APIs that are specific to certain providers. For example, Ollama. So earlier today, I showed the wasmCloud space demo, and that actually uses Ollama under the hood. Some key pros for Ollama. We've got so many different models there. A lot of these are open source models that you can pull down and run on your laptop. So the demo I ran was on my laptop with running Ollama with their desktop app. So it has a ton of different desktop apps for Mac OS, Windows, and Linux. So it's really great for consumer hardware. And it knows how to fall back to a CPU if it needs to. That makes it perfect for local model deployment and development, and makes it very, very easy to use. Now, there is a big con, although to be fair, this is a problem that we're trying to solve across the industry, and that's you can only run one inferencing at a time because it's kind of hard to figure out a way to multi-tenant your GPU. So if you're using Ollama, I really recommend it for local and edge applications. Understand that you're going to have some type of workload lock before executing on your GPU. So make sure that you think about that. And also understand that this is really a privileged capability. You're giving access to running inferencing on a GPU. And with wasmCloud, you're able to give that capability through a link. And I'll show a little bit of what that looks like inside the demo. Now, we're going back to the application architecture here, and I'm going to talk through this component specifically, the image analyzer component. It's the one that triggers our inferencing on, runs image classification against the image that we upload. There's another piece here that also uses a blob store bucket. But let's first run through and remind ourselves how this demo works. Again, I've got a globe. I'm going to use some different images this time. And the job of this image classifier is to determine whether or not this image is a ship. So I have a Corvette running on top of water, so it's kind of confusing. Let's see what the AI does here. Okay, this Corvette is not a boat. Let me give it a real boat. So this is an image of a boat. Let's see whether or not it determines that that image itself is a boat. Okay, it is a boat. Let's look at the code on what is making all of this happen. My component here is the image analyzer.wasm. It's 292 kilobytes, so extremely small. Compare that to a container that's in orders of hundreds of megabytes, even gigabytes. And what it's doing here, we're going to step through the logic a little bit since it's fairly straightforward. We essentially have it making an OpenAI HTTP call over to Ollama that's running locally. Ollama surfaces and supports OpenAI compatibility over HTTP. So if I'm configured to talk to an endpoint, I'm going to call that endpoint here. And then I'll also be able to pass in a prompt so that I can, configure this actually at runtime. So one little piece here, this code is WASI config runtime. So it's my ability to change and modify the config at runtime. And how do I do that? I do it by working within our application manifest. This is my component getting pulled from OCI, and here's my runtime config. And notice that I have a very simple prompt passed in here, but I can refine it and make it better at runtime as I want. And it's linked over HTTP, so that's the part that's making the request over to Ollama. And then it's also managing the tasks that I'm working with within this component. One other thing I want to highlight is that I did mention that the image processor, so once we've processed an image, we said, oh, it's a boat. Let's save it and process it later for more things. Let's upload it to a blob store. So I link it to a WASI blob store. But what's really cool about this is that I can actually use and swap in a capability, in this case, a blob store that's my local file system. That is really, really powerful because it means that I can take the exact same .wasm that I'm developing locally, working with Ollama deployed on my desktop, and then when I deploy it to production, it's still making OpenAI API calls. So I could back it by OpenAI provided by Microsoft. So, and also a blob store, let's say, with Azure. It's very, very powerful. One last thing I want to show here is that when I look at my component to see what it has inside it, I run this command called wasmTools component wit on top of my image analyzer component. I'm outputting it to component.wit, and you can see the things that it needs to be able to run. There's that WASI config runtime import, and then all of the other different WASI pieces that I use to be able to execute this component. So that is a very brief overview of how you can write your own component using Ollama and our Ollama provider.